I'm going to follow in the tradition. I'm going to follow in the tradition that we had from the first brain connectivity meetings, which was to give an update, not only on new ideas, but also on technical matters. I have to say that this is the work mostly of my students, Ming Li and his lady, Annie. This is my Chinese PhD, and another PhD from Cuba and his lady, and Anya just finished her master's in methods, all this in China. And I have to really pay tribute to them because during 10 months of this whole period, during the pandemic, I was in Cuba and we were working virtually. I managed to get to China where I am now. So this is joint work of the Cuban Neuroscience Center and the University of Electronic Science and Technology. And this is the symbol of my lab, which is, by the way, also the symbol of the third connectivity workshop. I have to say, I'm also very glad that Carl's presiding this, because I think maybe 10 days before the pandemic, we were planning on me visiting him in London, and then the borders closed. So some of these things were the ones I was going to discuss with him. Okay, this is going to be a technical talk, and I'm going to be talking about neural mass modeling. And in two directions: new methods that we have continued perfecting from our prior work, and second, the use of information theory to test the validity of some of the measures of looking at connectivity, of effective connectivity. And you might remember that we developed and presented in many of the other workshops a method for doing the integration of neural mass models by using differential algebraic equations. And let me explain this a bit. So this is the classical Janssen and Ritt model. And you can have many of these nodes. And the whole point of our differential algebraic approach is that if you take a sufficiently small time resolution for the integration of these random or stochastic differential equations, then each neural mass is essentially isolated, because the other neural masses have already produced whatever signals they're going to transmit. Therefore, we can solve each neural mass separately. And since it's a much smaller system, we can solve it analytically. And that's why we call it, differential algebraic method. Using this approach, well, Ming Li, that's her. She just finished her PhD last week. Very practically laude cum laude, and we were able to replicate using this method the classical Hopf bifurcation, which we had studied, for many years, since 1999. But importantly, we started looking at methods to try to find the underlying manifold, which is the low-dimensional manifold. And we can do this by working in the space of the eigenvectors of the backward Fokker-Planck equation. And this is a method that's been developed by Tal Schnitzer, and it has a connection because we use diffusion learning to project down to the lower space. Now, here we found a problem that when we started testing some of the models we were getting a bit of inconsistent results. And let me explain what they are. What we did was to start using a combination of information theoretic methods. There's a very nice suite which is called Tigramide, that's been developed for meteorology, but it provides a framework that achieves two things at the same time. One, it has very general, and you can add on different types of measures of association. And this is the first step. And what it does, since we're looking for causal diagrams, is to do a generalization of the PC algorithm that was developed by Spiritus and his colleagues, and which ensures that the causal diagram that comes out will follow the rules that are consistent with a possible causal diagram. In the second place, we then can use methods of transfer entropy, which can then give direction to the different links. And we use three types of methods. These are the ones that are embodied in the program. One is the simple partial correlation, if you think the model is correlated. Another one, which uses a two-step method, which is based on Gaussian processes, and then what is known as the distance correlation, which is a generalized metric of correlation. And finally, the more usual method used by many programs, which is the nearest neighbor measurements of transfer entropy through calculation, a very fast calculation of what is the conditional probabilities necessary to get the transfer entropy. And that basically what Anya, and that's her, she graduated also just very recently as a master's. What she did was to test several types of simulations, and none surprisingly. Of course, if we had a linear autoregressive system, the partial correlation did fine. And, it had, when you added noise, it wasn't as bad as the other ones. For, let's say, tailored, nonlinear autoregressive models that are multiplicative, the Gaussian process was okay. But the method that used the conditional mutual information based on k nearest neighbors, that worked practically well in all situations. Okay, now what was our surprise? And the purpose of me presenting a lot of this is to look for people. We're sharing the code, so we're rolling out all this code. If it's already either in GitHub or will be, and we're looking for collaborations to continue trying to find answers to some of the questions that we pose. So the first thing we did was to look at groups of Jensen and Ritt models that were interconnected. There you can see the general topology. This was a very simple toy system. And surprisingly, we found that the method that we had seen in previous simulations, that is to say, the conditional, the transfer entropy based method that was based on k nearest neighbors, when we did this type of narrow mass modeling, then we found that it performed rather poorly. So we were wondering who was the culprit, and I'll tell you, we think it was. And just to anticipate, we think it's the modeling of the delays between the narrow masses that seems to be creating the problem. So what we did was then apply the method that performed the best, which was the Gaussian process model. This is just to show that we were working with the Human Connectome project data. This is eyes open resting state. And we show on the bottom the reliability of this causal diagram searching method. It was pretty stable across different time segments. And we found, has been described by others, that the strongest connections were related to the visual area. So this is just to confirm that using the methods we have results very similar to those obtained by Christian Beckman, Pedro Valdes, and others. And so therefore, we think that our problem was not with the general methods, but with the narrow mass models we were employing. And I repeat, it's because of the delays. So here comes an extension of what I spoke about in Zurich. If you remember, in Zurich, I was saying that connectivity, effective connectivity, is a tensor problem, because you have emitter nodes, you have then receiver nodes, and then you have the delays between the emitter and receiver nodes. So what we did is that if we have a general narrow mass model, now, which we can express here, this is in the first formula, we applied the idea of turning it into a differential algebraic equation. And therefore, what we have is the state variable for all of the narrow masses. We have here the path that of input that comes from all the narrow masses, and it's already known at a given time. And then the parameters, and then what we call the connectome tensor. And the connectome tensors is the strength of connections, but it's the outer product with different types of delays. Now, here we have it. How we apply the connectome tensor. We have to use a tensor operation. This is very efficient computationally. We're implementing now on GPUs, and so it will be efficient. You have a window of time in the past that you have to keep track of. But in the simulations I'll show you, we tried 3 different types of distributions of delays between narrow masses. D1 here is just the usual, that there's no difference in time, there's no delay, it's just the direct centered at 0. We have D2 where we just shifted, and this is estimated by, let's say, the length of the path divided by the conduction velocity. So this is what is usual in many simulations, but more interestingly for us was the 3rd type of delay distribution, which we used a generalized gamma distribution, but it can be anything. And this comes out if you take the distribution of axon diameters, let's say, like Paul Newman did it once, and then you plug it into this equation and you estimate the probability density, you get out a gamma distribution of this sort. Now, when briefly, the first thing we tried out was to see, and I'm showing here just briefly, just a few nodes, but actually Anis Lady, who has been doing this work, she's here up in the right corner. This already works for thousands, very efficiently for thousands of narrow masses. So we tried 3 types of topology, one fully connected, on the other hand, let's say just nearest neighbor connection, and then a small world connection. And these are the connectivity matrices. What we found is that and I'm going to be showing only suppression of noise. I'm not going to be inputting noise, not to complicate the issue. We found qualitatively similar topology. These are topologically equivalent state space diagrams, okay? Where we have the potential in the pyramidal inhibitor is stellate cell for the, let's say this is the average for all of the 1,000 of cortical models of Jensen and Ritt units. And topologically, they're very similar for the 3 situations, but the nuances, there's nuances as to the actual, let's say, trajectory, which shows up in, as we will see later, in when we study different types of distribution. This is for a distributed distribution taken where the gamma activity is taken from the literature on axonal diameter. Okay, so we're going to concentrate on the small world, and what I'm going to show now briefly is what happens when you let's say, no delay between these thousands of Jensen and Ritt models, when you have a fixed delay, which is also a delta direct, but when you have then at the same peak, but you have a gamma distribution. And what happens is that, as I said, the spectrum looks pretty similar for all of them. Therefore, of course, the spectrum is looking at the first order characteristics of the Vita-Volterra expansion, and it's only looking at linear characteristics. We see the differences that I mentioned here also that are in the, let's say, in the state space, and the waveforms are slightly different. So we do believe that this might be a factor. And what goes now is that we're going to study this in particular problems. Michael Breakspear suggested that we try to look with these distributed delays at the split alpha phenomena in the EEG. And that's what we're doing now. Finally, I have to say, because I'm keeping this very brief, is that our next objective is to try to explain the development of the EEG. Relevant to this is work by Ming Li, in which we have gathered a database of approximately 1,700 subjects. We've been using Riemannian geometry to calculate from this multinational, it's 9 countries. And we've been calculating the developmental surfaces of frequency, log spectra versus age from 5 to 100 years. We have this for healthy subjects of these 9 countries. Currently, we're in the second phase. This is work of the Global Brain Consortium that I'm co-coordinating with Alan Evans. It's a global EEG norms project. By the end of the year, we should have tripled the amount of EEGs, and we should have roughly 2/3 with the accompanying MRIs and DTI. So the challenge would be to see if we can explain all these neurodevelopmental characteristics of the EE using this frame. So basically what I wanted to do is an update on the work that we've been doing. This will also engage with the virtual brain as part of the Highball project, which is being carried out between the Helmholtz Institute and the Montreal Center for Integrative Neuroscience. So that is it. Open for questions. Let me stop sharing.